All right. Good afternoon, everybody. I'm Sunil from AWS. I was the head scientist on DeepRacer here. So just wanted to talk a little bit about how the project sort of evolved and where we are at, but really focus on the simulation to real aspect with respect to deep reinforcement learning. Just to give a recap on what the product is all about, DeepRacer was actually built as an educational platform. We saw that reinforcement learning was not quite out there. We had lots of fragmented aspects with the tools that were available. And so we built the platform, SageMaker Reinforcement Learning Platform. And on the other hand, there weren't a lot of good materials in terms of practical reinforcement learning. So we want to bridge that gap, and that's how this project was born. Just in the context of reinforcement learning, what we consider an agent is this toy car, which is a 1/18 scale autonomous car. And you get to define an action space, and we've sort of only started with discrete action space to keep it simpler. Environment, in our case, is the track, the race track. And the goal is to go around the track, but specifically is in the shortest amount of time, so we have time trials. So let's dive into what the car sort of looks at. So to keep it simple, and we kept in mind that everybody who's getting into this is probably new to reinforcement learning, new to devices, so we wanted to keep everything extremely simple. So even though it was harder for us to build with this, we actually kept it as a single camera. So it's a single camera sensor that is giving the input into the car. And it's an open loop system. What that means is the car doesn't have actually a feedback when it makes its own action. So it has to really learn through only the sensor, which in this case is an image. So what you do is you train in the simulator. As you see, it looks similar to on the left. And you have the capability to do distributed rollouts, which is have multiple tracks all at the same time. And you get to define your deep reinforcement learning. There are two parts to it. One is the neural network. In this case, we use it's an image-based. We've experimented, and convolution-based networks actually work really good as feature embedders. And our state, as you see, is 120 by 160 image. Although the image is shown in color, we grayscale it, and you get to define the action space. And state prime is, again, another image after the car has taken the next action. But what's cool is we understand at scale how do you reduce the training time and how do you build robust models. So what we do is you have the ability to do simultaneous rollouts. That is, you can have multiple tracks, say one on carpet or different shapes with some crazy turns, all of that being incorporated. And this is how the training environment actually looks like, what you see on the left. That's how the simulation training environment looks like, and the corresponding physical track is on the right. As you can see, there are some perceptual differences as we can see as humans. And what we expose to our developers is a reward function. So as an entry-level developer, all you have to do is focus on the reward function to specify what behavior you want to see with the car. But as an advanced user, you can have your own DeepRacer stack, modify the environment, really go through every single detail, and build that. Quick overview of the architecture here is there are two components. One is a simulation piece, and the other one's the training piece. The simulation piece is hosted on AWS RoboMaker. It is hosted with the component is Gazebo, which is an open source 3D simulator. And we have SageMaker RL, which is the RL component, and it's training. So the images get generated in the RoboMaker 3D environment and get sent to the the reinforcement learning training algorithm, which is hosted on SageMaker. The car itself, I call this a mini desktop. So this is a desktop on wheels. It runs Ubuntu. You have complete root access to the car. memory of 4 gigs, HDMI, so literally a good amount of compute and capabilities for you to experiment with. And as I said, it's intentionally kept open. We want developers to go build on top of this platform. Let's get to the machine learning side of things a little deeper now. What we take is the filter input, which is a grayscale image. And the first component is the feature embedder. So we use the CNN as a feature embedder. And believe it or not, like a 3-layer CNN is just good enough for you to extract really interesting features. And then a very shallow policy network, which is just the dense layer, as you see here. And then finally, the action space at the end. All right. All good things start somewhere, and these are some of the first prototypes. Just wanted to show some fun videos. And the first experiment that we had to do once we sort of, the simulation works, is let's actually put this car on the track. And first test is, can it drive straight? So I got the car, but unfortunately I damaged the car. So the Wi-Fi chip on the car was broken. So I couldn't wait. And we just had only a couple of cars that was just really out of the factory. And then I went and searched for the biggest, longest cable I could get. And you can see here with a makeshift track. And you can see the car actually made it. And one of the interesting lessons is you want to keep it simple. When things don't work, you want to scale back and actually start from scratch. If you look at the car, you will see the car takes left, right. It doesn't go just straight. So what I did was I reduced the action space into 2 things to really understand that the car has to learn, and every time it does something wrong, it has to correct itself, which is why you made it into left-right action space, and the car was able to learn there. So let's think about what are the challenges in simulation to real. And for all it's worth, like you've seen reinforcement learning, the promise of reinforcement learning, and a pet peeve of mine is all you see reinforcement learning do is play video games. So it's really important to how do you take it to the next level. So the way to think about and at scale with reinforcement learning is 2 aspects to Sim2Real. One is the perceptual differences, or perception and dynamics. The perception, again, like in this case, this happens to be image, so I'm saying perception. But essentially, any sort of state representation that you can have, I would call that as perception. And what matters here is the sensor fidelity, right? If you are not able to capture, if I have a really shitty camera and I'm not able to capture what's in there, then I won't be able to actually represent my state appropriately. That's needed for navigation in our task. The other is you might not be able to really pick on every little thing that's required for your model. And the other aspect, which is on the output side, is dynamics, right? If you really can't model the physics of the world that you're going to deploy the model in, then it's unlikely that it's going to fail. Trust me, this has happened. For the longest time, we couldn't get the car to work. We did a lot of perception debugging. We did a bunch of things. And the car wouldn't just work. And then we finally got it somehow to work. But we had an upgrade to the car. And what happened was the weight of the car, we actually reinforced the chassis, and it increased by like 0.5 kilogram. And what happened was the car now didn't work. And guess what? Like, we hadn't modeled the mass and the change in friction due to the increased mass of the car. And now, so once we figured that out, everything was fine. And so we named that car Newton. So finally, we figured out friction. So thanks to Newton, we were able to proceed with further. Yeah, conventional approaches to Sim2Real is what people do is system identifications. You really debug, understand the components of the car or whatever robot that you're building, and calibration, right? Like, you want to get the simulator as close to the real as possible. Domain adaptation Again, you could do this on a network basis, so whether it's a cycle GAN or whether it's some sort of feature embedder that's agnostic to simulation and real images, you use that. The other common sort of approach is domain randomization. So you inject a bunch of noise in the system, and you force the network to learn something that is very specific and only common in those two sim and real domains. This allows you to generalize better. Now, where did that take us? This was sort of a very early prototype. You see, it's DeepRacer, but it's more like Deep Slow Racer. But that was a start. At least the car is moving. You can see it's staying on the track. Sometimes it needs a little bit of help, but it does its job. So where do you go from there? So what happens, right? A system's never going to be perfect. So it's really important to build a tool chain and systems around it that allow you to debug and understand components better. So first thing what I built was a heat map. So this is a grad cam, which is gradient class activation maps here. What this allowed us to do was actually look at what the car was doing based on an action. So if I was taking a left turn, what aspect was the car looking at? So this allowed us to better understand, and guess what? Our lab wasn't perfect. It was, let's just say, slightly messy at times. There were chairs, there were open windows, and when things didn't work, when we built this, we saw that, clearly the reflection of the sun was affecting. There was one particular box that somehow the model really liked. And so the moment we sort of covered things up, things got better. But this just allows you to do that, to debug. But as a consequence of these heat maps, what it allows you to do is really map your reward function now to the desired action. So that if you look at a sequence of images, now you can actually understand if your predictions are being matched. Like, is this a real reward function that it's learned to be? Another aspect is we came up with, okay, let's really understand the failure cases of the car itself, right? So the exploration-exploitation trade-off. If the car hasn't really explored, let's say, there's only one right turn, as you can see in this, going counterclockwise, there's only one right turn in the track. And if the car doesn't spend enough time there, probably it's unlikely that it's going to generalize. So identifying these sort of bottlenecks in terms of where the car or your agent has explored allows you to now understand what changes that need to be made in your reward structure or your training mechanism to better say Sim2Real. So as you can see, we generated these reward heat maps. So you have a good idea of where the rewards were awarded and what sort of paths, exploration paths, the agent took. It had some surprise implications, actually, when we built this and we generated. Clearly on the top, you could see there are rewards being assigned outside of the track. So guess what? Like, one of the engineers had implemented some of the math distance calculation wrong. So clearly that was affecting Sim2Real. So it allowed us to be like, okay, there's something wrong. Let's do the math again. Let's draw. We changed the method of how you basically we got more granular polygons to do the distance calculation, and you can see is a much more clearer reward heat map that you see down. Now this sort of allowed us to get better at reward transfer, simulation to real transfer. So on the left you see is a couple of laps that we ran in the simulation, and you can see the reward function here was follow the center line. And you see that the car pretty much really follows the center line. And then what you'll see is when we put the car on the track, the car actually does follow the center line. And I'll just wait for the turn as well. And you can see even on the turn, it really follows the center line. And a similar example here for where we say, hey, stay on the left lane. and you'll see that the car, even in the real run there, is staying on the inner lane. So yeah, where did we evolve, right? Like you saw, we improved, and finally we got to a point where the car, this is a real race. You can see this is the world champion for DeepRacer Summit, and the car is literally flying. That's the average speed of that car being about 3 meters per second. So, and that, if you multiply that by a real scale car, so 18 into 3, so that's 54 meters per second will be on a real car, and that's really fast. So, and you can see the consistency and the robustness is pretty high there, even at that speed. And what we've seen is, beyond a certain speed there, it gets a little tricky, and the chances of the car actually toppling on a radius, on the turning radius that we have there. Diving in deeper in terms of how do we go from there, right? Like we saw that, well, in this case, the simulation and the real environment looked really close. But what if there are lighting changes, right? Like what if I close all the lights, it's dark, and are we going to do the same? So it's just a little analysis that we did, which is we increased the brightness when you go from left to right, and you can still what you'll see is the left is the probability scores, and the right is just the unfortunately the background is a little dark there, but it's looking at the action space and what the action took. And what you'll see is there's consistent action being taken for the same image with different brightness levels, but you'll see one that goes down. The only difference there is the throttle is one is where throttle equal to 1 and throttle equal to 0.5, but the steering angle on both stay the same, which means that at least from a steering perspective, the car did want to go straight. Like the image only affected the speed, but it didn't affect the extra steering that the car would take. Same experiment here, except that we just added some gravel and noise here, and seemed like it was robust to that. So that was just a fun little thing, but then how do we, when we want to take it to the next level here? And the next level in this case was, let's add some fun lights. And you can see here what we call as multi non-focus lights. So we went to the store, bought some torch lights, placed them at critical points, especially the apex turns, to really affect and inject that. What we observed was when the broader light in the conference room was on, it really didn't affect. So we shut things down to really sort of, for those who drive here, right? Like we always hated when somebody is driving with their beamers on, like full headlight. It's not easy to drive. So same here, right? So we wanted to see what that effect was. So a bunch of single multi-focus lights, and then we got light array. So literally our lab was like a disco with all those fun lights. And then we wanted to see what the effect here was. And what we actually ended up seeing was, actually I'll just play the video first. The baseline train model usually could do fine, but sometimes it did have issues navigating. The disco lights was not a problem for pretty much all the baseline models that we tried. And then the focus lights, though, for baseline models meaning what I showed earlier, they didn't work all the time. So what we did was, okay, what is it that we can bring to the table ahead, and which brings us to attention. So we worked on adding attention to RL here. So zero-shot learning, which we did a benchmark with Darla, where the representations are learned independently. So they separate the perception and dynamics. So they train a variational autoencoder to understand what a track looks like, so an understanding of the world, and then use that in conjunction and train the policy. and then you combine both. So that's very disconnected process, but that was the state of the art, so we wanted to benchmark with that. And what we did was bring attention into the architecture that I showed you earlier and do a joint learning. And what we found out was we got much better focus. So on the left heat maps, you'll see the heat maps sort of spread out. And on the right column, you see attention, heat maps with attention, which are a lot more focused. And you can see the attention doesn't spread across beyond the actual track itself. And then on the right are the rewards. You can't quite see the graph with the scale there, but on the top, it's 700, and here it's 1200. So it actually, you see that the rewards are much higher with attention. And in the real test, what we saw was pretty much the method was on par or slightly better than Darla with all our experiments. There's a paper that we published at NeurIPS, actually, and that's available. The archive link is on top there. What's next, right? Like, what's beyond that? Multi-agent RL. So we wanted to bring that into the picture and have a platform to make that easy. So we go from a single camera to now multi-camera. So we have two. We have two cameras, left and right, and then we also added LiDAR capability because if you're really starting to do multi-agent RL and somebody's trying to overtake you, you can't see it. So you have a blind spot, so we added that. This is how it looks in the simulator. You can see the car, and the blue sort of, that's the LiDAR range. Here's how it looks in the real world. And you can see what you saw in that video was a real overtaking maneuver, right? Like it figures out that it can't go from behind, it makes a space, and then also behavior to sort of block the other car, but to actually gain speed. But multi-agent training is extremely hard. Like this is a video where it looks really good, but I would say there are still failure cases with multi-agent RL. Again, like that, as I said, like that's an open platform. We're open to more algorithms there. But we had a race a couple of months ago. It was a lot of fun, and really our job is to ensure that we can bring in the right set of abstractions and make it easier for you to do multi-agent RL. So we really wanted to kick it up a notch with the simulation to real aspect. So we did a challenge at the AI Driving Olympics at NeurIPS, where we kicked off a Sim2Real challenge. And before diving there, I wanted to showcase, so we run these summits, those videos that you saw are actual models that not we had built as AWS, but developers who had built, they come and race. So we have about 21 races across the world last year, and the final culminated in December at reInvent in Las Vegas. And by that time, we had about over 45,000 people, models trained, tens of thousands of developers who had built their models, many different countries, and a little metric of 165 miles across the track. And the track is only about 68 feet in the distance end to end. So as I said, like we wanted to kick it up a notch. So we give people a training track, but we didn't really tell them what the test track in the physical world was going to be. We told them that it's going to be a hybrid track. And what you see here is this track that they trained on was some wooden, some carpet, and some other changes. So first part was the change in the simulation. And what we did was as you saw with the lighting variations, we were like, we'll kick it up a notch. And unfortunately, we didn't have controls as we have in the lab to turn off. So what I did was I took a Scotch tape and like put it on the right. You can see in the image, and took a pen a felt pen, and actually made it darker so that we had some sort of lighting aberration there, so that now you had to not only navigate from, it's a heterogeneous track, right? Like one is vinyl, the other one's carpet, and it doesn't look exactly like it does in the simulator, plus the lighting. So this is what the track was, and the shortest path around the track was 11 meters, and the human benchmark. So there was an RC car driver there who was open to actually run it, and he did some benchmarks, so we just wanted to get a human baseline and see how fast he could drive. And he did about 10.89 seconds. And this track, the car had never seen before. And the RL model that one of our competitors built was able to do that in 8 seconds. And here's like, he got multiple. He got a couple of minutes to run the model, and this was just a video of that. And that's not fast there. There are a couple of laps. Just wait for it. So what's next, right? So we wanted to announce a challenge with AI Crowd. It's coming soon in March. So we'll continue the challenge, what you saw in at NeurIPS. So we'll continue that. So you'll have the simulation phase, where people will build the models and submit on simulator, and the top winners will go, and where we'll run a race in the lab and on a track that nobody's ever seen, and we'll see how it performs. Bunch of resources here to get started. We have a lot of free tutorials on reinforcement learning, build the models. So there's a free tier here. If you're a researcher, you've got access to the simulation assets, lots of tools, videos. I'll share my contact, and we've got GitHub link with lots of labs as well. We've had a couple of other folks publish. There's a professor at University of Cambridge who has worked on multi-agent augmented RL with DeepRacer. So open to collaboration here with folks. So with that, thank you so much. And I guess I have 1 minute, 49 seconds for perhaps a couple of questions.